Let's look at numbers 16 through 18 in your chemical equilibrium packet. In number 16, we have some concentrations that are given for each of the substances in our reversible reaction. We want to calculate the equilibrium constant after we write the equilibrium expression. So for the equilibrium expression, we always do products over reactants. The concentration of the HCl is in the numerator, and the concentrations of the chlorine and the hydrogen are in the denominator. The HCl has a coefficient of 2, so we are going to square that concentration. This is our equilibrium expression. Now we substitute the concentrations into our equilibrium expression and solve for our equilibrium constant. The concentration of the HCl is squared, and we substitute 0.0045 in for the hydrogen and the chlorine concentrations. Once we solve, we find the equilibrium constant is equal to 193. There are no units on the equilibrium constant, and sig fig wise, I am probably not playing by the rules here, but we'll go with 193. In the next one, we have some concentrations for our reactants and products at 1500 Kelvin, and we want the equilibrium constant at this temperature. Remember, equilibrium constants are temperature dependent, so if we have a different temperature, we will see a different constant. I'll start with my equilibrium expression and then substitute in my concentrations to solve for the equilibrium constant. Don't forget to square the nitrogen monoxide concentration. And we get 1.1 times 10 to the negative fifth. Again, no units on there. And because the equilibrium constant is so small, we would say that the reverse reaction is favored here. When the reverse reaction is favored, we see high concentrations of the reactants and low concentrations of the products. In the last problem on this page, we're doing something a little bit different. We are going to calculate the HI concentration given an equilibrium constant and the concentrations of our reactants. So here's our equilibrium expression. Plug in what you know. 54.34 for the equilibrium constant. Each of the reactant concentrations are 4.79 times 10 to the negative fourth. And then we're going to solve for x, but it's going to be x squared because of that coefficient of 2 in front of the HI. Once I solve for x, 3.53 times 10 to the negative third molar. This does need a concentration unit because we are solving for a concentration. Now we're going to do some equilibrium stoichiometry. With reversible reactions, we generally don't consider a limiting or an excess reactant unless the reaction is so forward favored, so product favored, that we don't consider the reverse reaction. So typically, we are going to have concentrations for all the reactants and the products. In the first problem, we want to calculate the value of the equilibrium constant for the reaction. We have to have equilibrium concentrations in order to calculate an equilibrium constant. You'll see in the problem, we have mention of an equilibrium concentration for C, but then we also have mention of the concentrations of reactants A and B initially. We're going to do what's called an ice chart. We use these to find equilibrium concentrations. I stands for initial concentration, C stands for the change in concentration, and E stands for equilibrium concentration. So A and B both start at 0.60 molar. That's the initial concentration for A and B. In the beginning of the reaction, initial concentrations for products usually are going to be 0. And then we're told C at equilibrium has a concentration of 0.2 molar. So I'm going to put that in the E row of my ice chart. This is everything I know based on what's given in the problem. Initial concentrations of A and B, and initial concentrations of C and D, and then an equilibrium concentration for C. Let's focus on C. How do I get from an initial concentration of 0 to an equilibrium concentration of 0.2? Well, that change, of course, is the addition of 0.2 molar. Think about this ice chart as if it's a little equation. 0 plus 0.2 gives me 0.2. Now, to figure out how the concentration of everything else changes, we're going to use stoichiometry. We're going to look at the coefficient ratio. So everything's in a 1-to-1 ratio. So if C increases by 0.2 molar, D also increases by 0.2 molar. And 0 plus 0.2 again, of course, is 0.2. So now for reactants. Reactants decrease in concentration. They get used up. So we're going to be subtracting. And again, everything's in a 1-to-1 ratio, so we're going to subtract 0.2 from each of our reactants. And 0.6 minus 0.2, of course, is 0.4. So now we have equilibrium concentrations for everything. And that's what we need in order to calculate an equilibrium constant. So again, reactant concentrations decrease throughout the course of the reaction, and product concentrations will increase throughout the course of the reaction. At equilibrium, none of the concentrations are 0. We're not talking about doing a limiting reactant problem. And now we're ready to calculate our equilibrium constant. Here's our equilibrium expression, the concentration of C times the concentration of D divided by the concentration of A times the concentration of B, so products over reactants. Substitute in the equilibrium concentrations and solve, and we get 0.25. So no units again on the equilibrium constant, and this is a fairly small equilibrium constant. We are definitely more reactant favored, and you can actually see that with those higher concentrations of the reactants. In the next problem, we have an initial concentration for the SO3 of 1.60 molar. Equilibrium concentration of O2 is 0.6 molar. We also know that initial concentrations of products should be 0. So here's what we know. We need equilibrium concentrations of everything in order to calculate an equilibrium constant. So 0 plus 0.6 gives us 0.6. Now for the SO2, we've got a coefficient of 2. So if oxygen with its coefficient of 1 is a 0.6 here for the change, then the change for the SO2 is double of that, plus 1.2. And 0 plus 1.2 is 1.2. Now for the reactant, which also has a coefficient of 2, we're going to be subtracting because reactants are reacted, and we're also going to be using the number 1.2. So 1.6 minus 1.2 is 0.4. We've got equilibrium concentrations. We're ready to write our expression and solve for our equilibrium constant. Here's our expression. Don't forget to square the SO2 and the SO3. Substitute in your equilibrium concentrations and solve. You get 5.4. Now in the last one, it's the same reaction, so same equilibrium expression. We've got equilibrium concentrations given. So SO3 and O2 are given as equilibrium concentrations. We also know initial concentrations for products are 0. So 0 plus 0.7 gives me 0.7 for my oxygen. And 0 plus 1.4 gives me my SO2 concentration. Again, it's double of the 0.7 because of this coefficient of 2 here compared to the coefficient of 1 for oxygen. I've got all of my equilibrium concentrations now, so I'm ready to solve for my equilibrium constant. Don't forget to square the concentrations of the SO3 and the SO2. And you get 5.5. This equilibrium constant is fairly close to the equilibrium constant that we calculated in number 2 for the same reaction. So you maybe could infer that these are pretty close to being at the same temperature. Equilibrium constants are temperature dependent. So if we have the same reaction and we get two fairly close equilibrium constants, we might say that they're pretty close to being the same temperature, if not the same temperature.